Hello everyone, welcome to the last differential equations lecture. I don't know whether to cheer or be sad, probably a little bit of both. It's been fun doing this, I hope I have been helpful for you guys. Alright, we're in 6.5, and lastly we're going to look at homogeneous equations. And it's a system of equations, I'm not going to do it. Homogeneous system of equations, linear, oh why not, I'll do the whole thing. Linear system. This time, instead of with real roots, we have complex roots. Okay. Homogeneous linear system with complex roots. Dun dun dun. Yes. So think about it. When we did homogeneous systems, homogeneous equations before, we had in chapter 3, we did first of all with real roots, and we did it with multiple roots, and we did that in the last chapter. Remember how we talked about, last section, we talked about geometric and algebraic multiplicity. That was the multiple roots. This time we're going to play with complex roots. So how do we know we're going to get a complex root? We're going to find that lambda is equal to alpha plus I, actually beta. This should be a beta. A cute fish, no. Alpha plus I beta. And our eigenvectors is going to be in the form of A plus IB. Now, why do I give you that? Well, I give you that because there's a very long, not very long, derivation in your book that actually I am going to skip. It's the end of the course. You can look it up in the book. When all is said and done, you're going to find out that you can write these two solutions. So basically, okay, this should be actually a plus or minus, right? We're going to get a complex conjugate, a conjugate pair of eigenvalues. So usually if you get an A alpha plus IB, you're going to get alpha minus IB. Why? Because remember, in the quadratic equation, we have negative B plus or minus the square root of B squared minus 4AC all over 2A. We're going to use that, once again, because we have complex roots. Here's the thing. There's that plus and minus. There's that plus and minus. It's the same thing. It's just basically we're going to get two roots from one equation. Once we do that, I mean technically you can put I minus or plus. We're going to find the eigenvalues. Once we find the eigenvalues, we're going to find the eigenvectors, just like we've been doing before, except now we have complex numbers. That's it. Everything's the same. This is a little twist because we're going to take the eigenvectors we get and make them into this shape. And lastly, we can then write our value. So we can say x1 of t is equal to. Now here's what we're going to write down. This is our general solution. Remember how before we had a e to the at cosine and e to the at sine. We're going to get the same thing basically here. E to the alpha t times cosine beta t times a. So vector a minus e the alpha t sine beta t times vector b. Okay, so there's that. Eigenvector b. Well, it's not an eigenvector anymore. We're taking the eigenvector and breaking it up into real and imaginary components. Okay, so that's x1. Now here's the thing. If we're doing x2, you know what, I'll just rewrite it. If we're doing x2, x2 looks quite similar to x1. So that's x1 for our eigen. So if we had complex eigenvalues, that's x1. x2 of t is equal to e to the alpha t sine beta t times a plus e to the alpha t cosine beta t times b. This is a beta. I know it doesn't look like a beta. Let me make my beta look better. If I can do this nicely. I would blame the marker, but we all know it's me. There's a beta there. And there's a beta there. There's better betas. Okay. So once I know A, B, alpha, beta, I can just write the general solution, the two solutions, and that could be part of the general solution at that point. Okay, so how does this whole thing work? Well, the whole thing, by the way, and then we can say that x of t is equal to x1 of t times c1 plus c2 x2 of t. So there's our general solution. By the way, we can come up with other weird things that happen, and I'll show it to you as we go through. We're going to just do examples, show how we can use what we've known so far, plus that extra little piece that we just learned, to be able to solve homogeneous with complex roots. Alright, so here it is. So we know that in this case a is equal to -1, -1, 4, -1. Okay? So that's a. Remember, if I was looking at this, it would be x prime of t is equal to a t. That's our general equation. Okay? So we're going to erase this back off, because we don't need our general equation. We need this piece. Alright, we're going to do like we just did last chapter. We need the determinant. We're going to try to figure out what the eigenvalues are. So, -1 minus lambda, -1, 4, -1 minus lambda equals, well, I get a -1 minus lambda squared minus a -4, which means I get a +4. Do this out, I get lambda squared minus 2 lambda plus 1 plus 4 equals 0. So I get lambda squared minus 2 lambda plus 5 equals 0. Alright. So if that's the case, what are we going to do? Well, we stick it into our square equation, quadratic equation. So we get negative b, so we get -2 times a negative b would be 2 in this case, plus or minus the square root thereof of b squared, so it would be 4, 2 times 2 is 4, minus 4 times 1 times 5, all over 2 times 1. There's our quadratic. 4 minus 20 is a -16. So if I take the square root of -16, it's 4i. So I get 2 plus or minus 4i over 2, which basically means it's 1 plus or minus 2i. Now, here's the thing. First of all, that 1 is alpha. That 2 is beta. So we got the first two pieces that we're worried about. Now, we have to stick one of those eigenvalues back into the equation. So we're going to leave that there. So we'll go back to our equation, and basically we have -1 minus, and then we'll put 1 minus plus 2i. Then this was -1, this is 4, and this is -1 times, -1 minus, -1 minus 1 minus plus 2i, sorry. I'm already thinking a step ahead when I actually do that. Alright, I'm going to erase this here. We'll get back to it in a little bit. Times xi1, xi2 equals 0, 0. Alright. So, basically here, let's just, this is one of the few times I think I'm actually going to do it out. 1 minus 1 is -2, so I get -2 minus 2i. Or did I make a boo-boo with my minus? Oh, it was -1. So we had a -1 plus 2i. And we're minus a -1, so there should be another minus here. There we go. My bad. So this is why I wanted to double check. It's very easy to lose stuff. So, -1 plus a -1 is, -1 minus a -1 is 0. So I get a 2i, -1 for 2i. And there should be a negative sign from the 2i. And we still have xi1, xi2 equals 0, 0. Okay? So I get a negative 2I plus xi1 minus xi2 equals 0. Likewise, I get a 4 xi1 minus 2I xi2 is equal to 0. And I'll tell you, both these equations are exactly the same if you multiply. Wait. Yes, because if I multiply it by 2I top and to the top, I would get negative 4 times I squared, which is a negative 1, so I get a positive 4, and I would get a negative 2I up here, which would be the same as here. So they'd be the same equation. Okay, so I can solve for one of them. I'm going to just solve the top one, because the top one seems to be the easiest one to do. So therefore, xi2 is equal to negative 2I xi1. So the vector, if I was doing the vector, xi1 is equal to, now, if I let xi1 equal 1, xi2 is negative 2I. Alright, we're almost done. This is why this technique is wonderful. Okay, so our eigenvector, remember we had this, alpha was equal to negative 1, beta was equal to 2. Now, we have to transform this into that a plus b. So we're going to say xi1 is equal to, what we have here, 1 negative 2I. Well, what did we have as a form? We said we wanted it in terms of a, so we have some real component plus I times b, which is some component here. Well, what's the real component here? We have a 1 and no real component down below, because we're going to add a real component. Here, we want the imaginary component, so we have a real component, that goes to 0, and the imaginary is negative 2. So this is A, and this is B. So we have alpha, beta, A, B. We can write the general solution. So, when we do that out, we're going to say that x1 of t is equal to. So if we have E did I get it backwards? Wait a second. I erased my equations. I apologize, people. Alright, so let me go back through. So I had negative 2I. So there's a negative sign here that I screwed up. Ugh. I don't want to start again. Alright, let's just... I'm going to write down the equations I had in my book. Well, hopefully they're the equations here. We'll leave this up here for just a second. It's just a sign problem that's an issue. And I know it's going to pop up. So, I would have had negative 2I xi1 minus xi2 is equal to 0. That's what I had as one of my things. I bring it over here. Negative xi2 is equal to 2I xi1. No, it's all set. So when xi is 1, we get a 2I for xi2. Oh, this is complex conjugate thing coming back to haunt me. Okay. There's a couple different ways you can do this. If I let xi equal 1, xi2 would equal to, so I gotta bring a negative over, we had negative 2I. Everybody sees that, hopefully. So I would get this vector. That vector is the same as if you multiplied this vector by I, which could be part of the constant. 6 of 1/2 does another. I'm going to stick with my answer. It's not going to be the same as the books because the way I did it, but that's okay. So we'll go with what I had. I just showed you how if the constant, if you have an I in the constant, you could go ahead and get that back out. So let me just show you the following, how I would finish this up. So, with this being the case, I can then write that x1 of t is equal to, so we go ahead and we start writing it out. It's e, the alpha, so alpha is minus 1. So e to the negative t cosine of beta, which is then 2 times t, times vector A. Minus e, now alpha, oh, that's why they did it that way. Who cares? E to the negative, oh, sorry, this is minus, e to the negative t, because that still holds true, sine of 2 beta, of 2t, sorry, times its vector, 0, negative 2. So if I really want to write this in vector form, I can do so. I'll show you that really quick. And we'll do x2. So x1 of t equals, well, if you think about it, it's this times this, so I'd have this on top, minus this times this. So I'd have this on the bottom. So basically what I end up getting is this. E to the negative t cosine 2t, and then I would have here, so I have a negative here, times a negative, so basically I would then have e to the t sine 2t, negative t, it should be a negative sign. That'd be x1 of t in vector format. x2 of t would equal, well, we know it's e to the negative t sine 2 beta t, so this would be 2t, plus, oh, I forgot the vector, 1, 0, plus e to the negative t cosine of 2t times this vector, 0, negative 2. So if I rewrote that in terms of being a vector, we have the 1 on top, this is the minus 2 on the bottom, so therefore I would then get x of 2 of t is equal to, the top would be e to the negative t sine 2t. The bottom would, I have a negative 2, so I get a negative 2 e to the negative t cosine 2t. So there's that one, there's that one. And then if you're putting it all together, I'm not going to do it on the board because I ran out of room, but x of t is equal to, remember, c1 x1 of t, and yes, I would make you write it out, plus c2 x2 of t. This is what I'm looking for when you substitute in the actual, actual vectors into their supposed spots. You do not get to get away with that on your test. I do, or on your quiz. If I put this on your quiz, okay. That is it in a nutshell. I mean, that we're going to do another couple examples, but that is it. Oh, I forgot the 2 up here. There should be a 2 up here because we had a 2 on the bottom. Jeepers, I'm dropping stuff all over the place. Let us do one more. And we will be done. Done, people! Except for testing for you and grading for me. But all new material will have been gone over. Alright. For our last example for the course is equal to, so we're going to use this equation. 1, 0, 0, 0, 0, 2, 0, negative 2, 0. This is a very sparse matrix, which makes us happy. So if we're going to write this in terms of what we're going to do for our finding our eigenvalues, 1 minus lambda, 0, 0, 0, 0 minus lambda, 2, 0, negative 2, 0 minus lambda. There's a whole set of math about sparse matrices. I don't know it. I just deal with some of it. Okay, so if that's the case, I can write the characteristic polynomial. So it's going to be this times that square. So we have 1 minus lambda times, well, this is lambda squared minus a negative 4, so plus 4. And then this is 0, and this is a 0. So therefore, that's the only thing we have, equals 0. So if I play with this, I get lambda squared plus 4 minus lambda cubed minus 4 lambda. Not x. Lambda. So if I play around with that equation, where's my lambda cube? This is my lambda cube. So if I play with this equation, I get so if I factor out, let's see, what do I put out? How did I do this? So 4 lambda that I didn't deal with. I jumped a step, and I'm trying to figure out how I jumped the step. Alright. So, let's go ahead and deal with this. So we have here lambda squared plus 4 minus lambda cubed minus 4 lambda is equal to 0. So, therefore, I can go ahead, you'll have to trust me on this one. I have a 1 minus lambda in this thing. I'm not going to show the division. And after I do that, I am going to get out a lambda squared plus 4. I thought it easily factored. It doesn't, so that equals 0, by the way. So therefore, I have lambda equals 1 for that root. So lambda 1 is a real root. Woohoo! Lambda squared plus 4 is a root, but it's a double root. Well, we got lambda 1 is going to be equal to 2i. I mean lambda 2. And then lambda 3 is going to be equal to negative 2i. And both those satisfy that lambda squared plus 4 equals 0. Alright. So if we're doing the real root, let's do the real root first because it's fun. So we have here 1 minus 1, 0, 0, 0 minus 1, 2, 0, negative 2, minus 1. That's what we would have. We're putting in lambda is equal to negative 1. Our usual xi1, xi2, xi3 equals 0, 0, 0. Alright. So here's the cool thing. So we do this out. So we have 0. So you'll see xi1 has no factor because all the things xi1 is going to multiply is equal to 0. So we don't care about it yet. We have negative xi2 plus 2 xi3 is equal to 0. We have negative 2 xi2 minus xi3 equals 0. That's really hard to do. But the only way these two equations can be the same is if xi2 equals xi3, which equals 0. Xi1 could be anything. So therefore, my first vector is equal to, we have 1, 0, 0. And you can have a C1 here if you want to. Yeah, there's our first vector. Our first vector is 1, 0, 0. Alright. Time to use the 2i. So this becomes 1 minus 2i. This becomes minus 2i. This becomes 2i. Or does it? No, it doesn't. I was just trying to trick you. Alright. So if we do this out, we look at this. We have 1 minus 2i times xi1 is equal to 0. Then we have 2i times xi2 minus 2 plus 2, sorry, this is minus 2i, plus 2 xi2 is equal to 0. Sorry, let's try it again. Xi2, xi3. Oh, that's a horrible thing. Xi3. Alright, and then finally we have minus 2 xi2 minus 2I xi3 equals 0. Now, once again, if you multiplied this equation by I, by negative I, you would see the fact you get a positive 2 out of here. We get a negative 2 like we expect, and we get a negative 2i over here. So these are two of the same equation. So we can drop the 2's, and we can say that xi2, so yes, xi2 is equal to a negative I xi3. Okay. Checking out one thing really quick in my notebook. Alright, now let's look at this first equation. 1 minus 2i times xi1 is 0. That can't happen unless xi1 equals 0. So we now have our vector. I'm not sure I have the right one this time. Alright, we're going to take their thing. So we're going to do the opposite. By the way, like I said, either one works. So if xi3 was I, you'd have I times I would be negative 1 times a negative 1, which would be 1. So therefore we can say xi2 is equal to 0, 1, I. Alright, well that's cool. So we have that. Now we can play one more game. The one more game we can play is the fact we have to break it up. Remember, we already have, so we said that lambda 2 was equal to 2i. So therefore, if I want to write it in terms of conjugates, I could say that alpha equals 0 and beta equals 2. Because of the 2i, there's no real component. That's why alpha goes to 0. The imaginary component's 2. So I have alpha and beta. We have to get this piece now in terms of a and b. So this is going to be equal to, well, once again, I'm going to have 0, 1, 0 in the real component, because that's the only real component I have, plus I times 0, 0, 1. So that's the only non-component. So this is A, and this is B. Now we can stick it into our big equation. I just erased alpha and beta. Remember, alpha is 0, beta is 2. So if we put in our big equation, we can say that x1 of t is equal to, well, it's going to be e to the 0t cosine 2t times a, 0, 1, 0, minus e to the 0t sine of 2t times 0, 0, 1. Which then I can rewrite, basically, so I have cosine 2t in the middle, sine 2t on the bottom. So I would get a 0, cosine 2t, sine 2t. x2 of t is equal to, well, we're going to have the same e to the 0t, so I'm just going to drop it out now, and I'm going to have here sine 2t times 0, 1, that's a horrible 0. Where I put my little eraser, there it is. 0, 1, 0, plus cosine 2t times 0, 0, 1. So therefore I can get x2t is equal to, well now, once again, I'm going to have the, oh man, I'm going to erase. Of course I erased what I was just about to write down, but that's okay. You have it on your books, hopefully. x of 2 of t is equal to, when I do this whole thing out, I basically get, oh, I forgot the minus sign. I forgot the minus sign up here. This should be a minus sign 2t. I get a 0, I get a sine 2t cosine 2t. So therefore, if I was going to write the whole entire thing down, which I should, I will get the following. Alright. X of t is equal to, well, we had a real root. So c1 e to the t times 1, 0, 0. Plus c2, this one, all those, we had 0, cosine 2t, negative sine 2t, plus c3 times 0, sine 2t, cosine 2t. Your homework for this section, 1, 3, 6. I hope you got a lot out of this course. I really wish I could have done 6, 6. I'm just worried about adding even one more thing to your plate just before final exam week, for final exam day on Thursday. I want you to practice these problems because some of these are going to show up on your exam. If you're interested, the next chapter is sort of cool. Next section is sort of cool. It brings to account the fact that then you could put in non-homogeneous solutions, and it would be the equivalent of 2 and 3 put together, but with matrices. But that being said, take care. Once again, just so you know, some people I know dive just to take a look at the homework. It's 1, 3, 6. I'll leave that on the very last. I hope you had fun, and do well in the final, please. Make my life easy. Make your life easy. Take care. Bye.